Okay, when we were last speaking, we were able to come up with an equation, an energy balance equation, the first law equation for a control volume at steady state. And what we observed was that the heat transfer from to the control volume and the work from the control volume, those two terms are then balanced by the differences in the enthalpies between the reactants and the products. And so if we were to consider the products, and in this case for our generic hydrocarbon type of combustion model that we have introduced, if our products take on certain mole numbers, and if we were able then to determine the enthalpy of the products at some product temperature, and then if we were to compare those, that H bar subproducts, the underlying grouping there, if we were then to compare that to the enthalpy associated with the fuel and the oxidizers, and in this case that would be the reactants, and the first law then would say that the difference between those two enthalpy terms for this flowing system, assuming no kinetic or potential energy differences, would simply be equal to the heat transfer and the work. And so we saw that each of these terms, each of these enthalpy terms, consisted of both a heat of formation value as well as a value associated with it being at some temperature other than the reference temperature. So in a situation like this, one of the interesting things that we are always looking for is what is this temperature of the products? And so one way of determining that is to assume we did not have any work that's being pulled out of the fluid, out of the working fluid, and assuming that the heat transfer was zero. In that case, it would be an adiabatic process. And so under an adiabatic process, we see that the left-hand side would be equal to zero, and our right-hand side is just products and the reactants. And so we could say that under an adiabatic condition, the enthalpy of the reactants would be exactly equal to the enthalpy of the products. Now that's only going to occur at one temperature of the products. And so when we are doing a problem like this, and we wanted to know for this combination of fuel and oxidizer, under adiabatic combustion conditions, what is the temperature that the combustion gases have to come out at? That would then be referred to as the adiabatic flame temperature. And so in essence, what the adiabatic flame temperature is all of the heat released by the fuel as they're being oxidized goes into raising the temperature of the products. And so in an adiabatic flame temperature type of calculation, we look for that single temperature such that the product's enthalpy, all summed up for all of the products, is equal to the enthalpy of the reactants. When we look at this conservation of energy, and again, in the form that we developed earlier, where we had the various stoichiometric coefficients, and again, these stoichiometric coefficients are available to us upon balancing of the hydrocarbon fuel equation. there are some heats of formation that we know go to zero, and those are the ones associated with the oxygen as well as the nitrogen. For the nitrogen case, that heat of formation shows up in the reactants calculation as well as in the products calculation. But generically, what really happens is that the heat transfer and the work combined is related to the difference in the enthalpy of the product and the enthalpy of the reactants. And each of the products has a heat of formation minus or plus a additional enthalpy associated with whatever temperature the products are at. And the reactants, the same thing holds. Depending on the fuel and the oxidizer, we might have a heat of formation or we might not. And then we have a delta H for each of the individual reactants depending on what temperature we assume the fuel and the air comes in to the combustion chamber relative to the reference temperature associated with the formation process. And so I just indicated that if this left-hand side is equal to zero, the temperature that we would then determine for the products would be referred to as the adiabatic flame temperature. Now, another important property is that if we allow the combustion to occur, and if we said that there was no work associated with the control volume, if we allow the products to come out at the temperature, a reference temperature, very much like the formation process, if we allowed the reactants to come in at some reference temperature after the combustion occurs and all the heat is released, if we take out enough energy from the control volume such that the products come out at the reference condition, we then would calculate a certain amount of heat that would have to be removed from the reaction. And that's a term that we use for what is referred to as the heat of combustion. And so we have a certain fuel, and when that fuel reacts completely, let's say, with air or oxygen, we can then say that in order for the products to come out at some reference temperature, a certain amount of heat must be removed from the process. Now, in the textbook, they also look at what happens if you have a reacting system and you are in a closed system. Okay, the difference between an open control volume system and a closed system. In a closed system, we have heat transfer and work, but we also have the left-hand side of the first law is written in terms of internal energy for the closed vessel. And so that those internal energies would be related to the individual components' internal energy. And since we know that there's a relationship between the internal energy and the enthalpy, and that relationship is H minus PV, or the flow work term. And for an ideal gas, we know that PV is equal to RT. And so by looking at the products here as well as the reactants, for the enthalpy, or for the internal energy, we can substitute the enthalpy like we had before, but then we have this additional term that corresponds to the PV term associated with the enthalpy. And so for a closed system, the heat transfer and work would be related to the differences between the reactants and the products, but now it's the enthalpy minus an additional term. And since this enthalpy is related to the heat of formation and the delta H, as we saw before, this equation here should be looked at in terms of this particular condition. And since we are dealing with ideal gases, and we see that the products, there's a number of each of the products and a number of each of the reactants, what we see is that this RT term and this RT term here actually can come out and be associated with a combined number of products and number of reactants. And so if we have situations where the number of products and the number of reactants are similar to each other, we then have a simplification of this term right here. And so this would be a case where we put the fuel and the oxidizer into a closed vessel. We have a spark of some kind to permit the oxidation to occur, and then what happens is all of the heat is released due to the rearrangement of the molecules, and the amount of heat that is generated by the heat release either goes into the final temperature, or if we bring the final temperature of the products down to some reference condition, the amount of heat that we had to remove from this system would be its combustion heat. So as I said before, this enthalpy of combustion, or sometimes referred to as the heating value, is the value associated with the differences between the products and the reactants. And if we allow the products to go down to the temperature associated with the reactants, this heat would be referred to as the enthalpy of combustion, or the heating value of the fuel. Now, in your various tables, you'll see that this value is listed, and it's listed as two different values. One referred to as the higher heating value, and the second, which is referred to as the lower heating value. And the difference is the higher heating value has, in the products, the water has been allowed to drop into the liquid phase. And so there will be an extra amount of heat that is released from that reaction, assuming that the products come out at a liquid condition for the water. The lower heating value would be a slightly different value, assuming that the water in the products come out as a gas. And so we finish up this chapter then with just a summary and review of the pertinent equations. Before I leave, I wanted to bring up the thermodynamic data that's again in the back of the textbook. We've already observed this. We talked about this earlier. We showed the formation process. We also showed the definition of what the enthalpy would be at a particular temperature and a pressure. And then we also wrote the first law equation representing the heat transfer, the work, and the products and the reactants. And so what I said before is if one allows a particular fuel to oxidize completely, and if one allowed the temperature of the products to go down to the reference condition, the amount of heat on a per mole of fuel basis that's released is called the heating value. And in this particular table, there is a line that corresponds to the heating value. Again, the higher heating value versus the lower heating value. The higher heating value is the value obtained if you permit the water coming out of the products to be a liquid, whereas the lower heating value is if you allow the water in the products to be gas. And so, for instance, if I were to go to, let's just use our standard methane. Methane as a fuel, CH4, we know that when it reacts with air, there is oxygen associated with the air, and in that particular case, when we balance the reaction and have CO2 and water in the exhaust or in the products, if we then allow those products to go back to the reference condition that the fuel and the air was at, the amount of heat that would have to be pulled away is the heat of the higher heating value and the lower heating value. So what you see is for methane, 23,880 BTUs per mole of methane would be released or would have to be pulled out of the reaction vessel in order for the products to come out at the reactant or at the reference temperature. And if we allowed the various products, the water to come out as a gas, it would be a little bit less energy that we would have to pull away. And once again, the difference between these numbers corresponds to the latent heat of the water. And again, these numbers, as you can see, are on per BTU per pound of the fuel itself. And so one has to be careful. In this case, here's methane, and methane is 16.04. That is the pounds per pound mole. That's the molecular weight. And so these terms for the enthalpy of formation was in BTU per pound mole. And once you used all of that with the reaction equation, the stoichiometric reaction equation, you would then find for 1 mole of methane a certain amount of heat that would have to be removed, and then one would then divide that amount by 1604 because that's how many pounds are in a pound mole, and one would then be able to obtain those numbers. And so for the various components here that typically act as fuels, we see that we list the higher heating value and the lower heating values associated with those fuels. And so in essence, it's basically just telling you how much energy is bound up in that particular fuel molecule, such that when you bring in the oxidizer in the form of air to oxidize and to split up those fuel molecules and allow those fuel molecules to release energy as they form CO2 and water, one then finds a certain amount of heat that can be released. Since we may be wanting to talk about the ethyl alcohol, or in this, ethanol, which is one of these two down here, we see that the heating values are relatively smaller than some of the heating values up here. Again, keeping in mind that these are on a per mass basis, a per kilogram or pound basis. Even though octane itself is a much larger molecule, you see that on a per pound basis, it releases a lot more energy than we see for a ethanol type of molecule.